squared plus k minus 2k squared minus 7k minus 3 all over k squared plus k, the whole quantity squared. Simplifying that, combining your like terms, this k squared and this negative k squared will make negative k squared. This k and this negative 7k makes negative 6k minus 3 over k squared plus k, the whole quantity squared. Now looking at this numerator, k squared is itself a positive value, but when you negate it, this is now negative. I'm taking a negative value. We also know that k is going from 1 to infinity, so the only possible values for k are positive. So negative k squared is now negative. Negative 6 times a positive number is negative, so this is even more negative. So ultimately, the numerator is completely negative, and the denominator is always positive because it's squared. So this, even if it weren't squared, k squared plus k would still be positive, but that's now obviously negative, which means this is decreasing. And now the easier thing to show is that this limit is 0. This is k plus 3 over k squared plus k, and again, I think we all know by now that when the degree of the numerator, oops, I meant to just point, when the degree of the numerator is lower than the degree of the denominator, this limit is, oops, 0. So yes, we now know from the alternating series test that this series converges. Next, we'll talk about a couple definitions. A series converges absolutely if the absolute value of the series converges. For example, the series from k equals 1 to infinity of negative 1 to the k plus 1 times k squared, 1 over k squared. So think about all this is saying to you. This is simply saying if I take the absolute value of negative 1 to the k plus 1 times 1 over k squared, that will, the absolute value bars invalidate the negation. So this is really 1 over k squared. There is no more alternating. Since the sum of 1 over k squared, oops, I should have had some here. Since this is a p series with p equaling 2, this series converges. Since the absolute value of the original series converges, it converges absolutely. On the other hand, the following series converges what's called conditionally. So if a series converges when there is no absolute value bars, but diverges when there are absolute value bars, it's said to converge conditionally. So for example, the series 1 over k, we looked at that previously 2 examples ago. The alternating series converges because it's decreasing and the limit of 1 over k is 0. So the alternating series converges. However, if you take the absolute value of that series, if we take the absolute value of this series, again, that nullifies the negative component of it, and you are now looking at just the series 1 over k, which is the harmonic series It's a p series with p equal to 1. So when you take the absolute value of that series, it diverges, but when you look at the original alternating series, it converges. That's called converging conditionally. we now have a theorem. This theorem states if the absolute value of a sub k converges, then the sum, there should be a sum here. If the sum of the absolute value of a sub k converges, then the original series also converges. In other words, this means absolute convergence I don't know what I just did, sorry. Absolute convergence implies convergence. Here's the proof. Suppose the sum of the absolute value of a sub k converges. So then the sum of a sub k without the absolute value bars is equivalent to, and this might be odd, but you'll see where we're going, the sum of a sub k is equivalent to adding on the absolute value of a sub k and then subtracting it off. The part that we're interested in here is right there. A sub k plus the absolute value of a sub k. Now, if a sub k is negative because it's an alternating series, the absolute value of that is positive. So this ends up being double. Or if one is negative and this one's positive, well, what I'm saying is if they're both positive, it's equivalent to 2 times the absolute value. If this one's positive because it's an absolute value and this one's negative, you get a 0. So that implies that this thing right here is between 0 and 2 times the absolute value of a sub k. So the sum of a sub k plus the absolute value of a sub k is less than or equal to the sum of 2 times a sub k. Now, because we know from the beginning, right here, that the sum of the absolute value of a sub k converges, that means that this too converges. Even though there's a multiplier of a 2 here, that doesn't matter. You can take the 2 out, that will still converge. If that converges, by the comparison test that we learned last time, we now know that this converges. But that is actually 2 series being added together. We know that this one's a convergent series. For 2 series to add together to still converge, they both have to converge. So this implies that a sub k also converges. Ultimately, all we're saying is that if a series converges, absolutely, that implies the series converges. Now here's an example. We have this alternating series 1 minus 1/2 minus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th, which looks very much like a geometric series, but there is no pattern to the positive and negative coefficients. So we really can't even write this as an appropriate alternating series because it's kind of random. So instead, we can try taking the absolute value of each term. If the absolute value of the series converges, then the original series also converges. So since this series is now really an alternating, a geometric series that's not alternating anymore, this is 1 plus 1/2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th plus 1 over 2 to the 5th, so on and so forth. This is a geometric series with a equaling 1 and r equaling 1/2, which implies that this series converges. Since the absolute value of each of the terms of this series creates a convergent series, that implies that the original also converges. Okay, now we'll look at an example. Another example. So the cosine of k over k squared. Now, it may not look immediately like an alternating series, but if you think about it, it is. It's because the cosine of 1 is in quadrant 1, because 1 is, pi is about 3.14, so pi over 2 is 1.5 something. So an angle that's 1 radian is smaller than pi over 2. So this is in quadrant 1, and cosine is positive there. The cosine of 2, that is bigger than pi over 2 but smaller than pi, cosine is negative there. Cosine of 3, again, that is in quadrant 2 because it's smaller than pi, it's also negative. The cosine of 4 is bigger than pi. In quadrant 3, it's negative. The cosine of 5 would bring us back to being in the fourth quadrant because it's bigger than 3 pi over 2. So you can still see that this is an alternating series. So now instead, let's consider the sum from k equals 1 to infinity of the absolute value of the cosine of k over k squared. The absolute value bars will not affect the k squared because k squared is always positive, so we can pull the k squared out of the absolute value bars. Oops. Now, what do you know about the cosine of k in terms of its potential values? Cosine and sine both can only ever range between -1 and +1. So if you're taking the absolute value of cosine of k, its largest possible value is 1. That implies that this is less than 1 over k squared, right? Because cosine k is between 0, absolute value of cosine of k is between 0 and 1. I'll say that here. So I guess technically it's less than or equal to 1 over k squared. Now, 1 over k squared, again, is a convergent p-series. And by the comparison test, if the bigger series converges, the implication is that the smaller series, which is this series, But that wasn't actually what we were trying to prove. We took the absolute value of the original series we were looking at. The original series was this up here, but we checked this series, which converged. So if the absolute value of the terms of a series converge, the original series also converges. So this actually implies that this series also converges. We will revisit this series that we looked at in the beginning of the lecture. This series, we decided, converges by the absolute value, the test for absolute convergence. I'm sorry. It's an alternating series, and it converges by the alternating series test. So we had to show two things. One, that the series decreased. I can't write again for some reason. Which we did show by doing the derivative. If you like, we could do it again, but I think that we don't need to do that. We did this at the beginning. We showed the derivative was less than 0. It was actually, oh, that was a different series. Let's take a look at another series. We looked at something similar to